Okay. I think in yesterday's class, 8.1, 2, and 3 were completed, right? Was somebody there in yesterday's class? Because when I saw it was like till 8.3, it was over. So can we start with 8.4? Can we start with 8.4? Okay, fine. Yeah, because see, when I saw yesterday's live session, it was like they were doing, Pranjal was doing 8.3. Okay, in the last few minutes, he was doing 8.3. That's why I'm asking if I can start with 8.4. Okay, fine. Yeah. So 8.4. So hope everybody knows about projections, right? Everybody knows how to project, right? Project onto a line or project onto a plane in R3. Okay. Hope everybody knows. If you know, I think it'll be easy for you. Anyways, while doing this, we'll just cover those. Okay. We'll start with 8.4. So in 8.4, they have given a basis, okay? Gamma. And the inner product space, consider the basis for an inner product space, okay, of R3 with respect to dot product. So the inner product here will be the dot product. Okay. Now B1 is 1, 2, 3, B2 is 1, 1, 1, and B3 is 0, 2, 1. Okay. Now beta A1, A2, A3, it's an orthonormal basis. Okay. Orthonormal basis means in this set, this will be the basis set. Every vector is orthogonal to each other. Okay. And the length of every vector is 1. Okay. This is what we mean by orthonormal basis. Okay. So we have to find this basis, okay, using Gram-Schmidt process. All right. So from this information, we have to answer question 1 and 2. Okay. Question 1 is what is the vector A2, and the question 2 is what is the vector A3. Okay. So first, the the set which we are given is 1, 2, 3. Okay. 1, 1, 1 and 0, 2, 1. 1, 2, 3, 1, 1, 1 and 0, 2, 1. Okay. Fine. Now, how do we find an orthonormal basis for this? How do we find an orthonormal basis for this?
Divide with norms.
Yeah, but dividing it with its norms can be done at the last step also, right? See, like for example, vector, let's say U is an unit vector, okay? Let's assume this. And let's say vector A is orthogonal to this, which means A dot U will be 0, correct? The dot product between A and U will be 0. Now let's take some scaled version of U, let's say 5U. If the dot product between A and U is 0, then dot product between A and 5U will also be 0, correct?
Yeah.
So we can, you know, uh, convert it into a unit vector at the last step also, right? See, like this thing, if these two are, if this vector and this vector are orthogonal, then this vector and this vector are also going to be orthogonal, correct? So we can adjust the lengths at the last step also. Am I right? Okay. So first thing what we will do is we will project B2 on B1. Okay. Now B1 is a vector, right? Now B1 will span a one-dimensional vector space in R subspace in R3, correct? In R3, let's say this is B1. Then an entire line will be spanned by this 1, 2, 3. Am I right? So there will be B2 here. We have to project this onto B1. Okay. So how will we project? How will we project? See, there's a line, okay? B1 is your line. Like B1 is your vector, and the span of this is going to be a line in R3. Okay. Now any vector in this line is going to be a scalar multiple of B, correct? B1. So it is going to be some P times 1, 2, 3, correct? Any vector in span of 1, 2, 3 is going to be a scaled version of 1, 2, 3, correct? Some scalar multiple of 1, 2, 3. Okay. Now if you are projecting B2 onto the span of 1, 2, 3, then that will also be some P times 1, 2, 3, correct? See, projection of B1 on span of projection of B2 on span of B1, okay, will be some P times 1, 2, 3, correct?
Yes.
Right.
Definitely.
So this is going to be some P times 1, 2, 3. Now, what is B2 minus P times 1, 2, 3? This is the error, right? This is the error vector. Am I right? Everybody
Yes.
knows, right? See, like you have two vectors. The addition of these two is going to be here, correct? The addition of these two is going to be here. Let's say this is B1, B2, B3, right? So B1 plus B2 is going to be B3, okay? Then B2 minus B3 will be what? B1, right? Or B3 minus B2, okay? B3 minus B2 is going to be B1, correct? Right? So similarly, we have P times 1, 2, 3, and we have B2. Now the projection of this vector onto the span of the first vector B1 is P, right? The projection. I think I'm not like the space is not enough. So I've drawn it like this. So this will be B2, this will be P, and then where will the error vector be? The error vector will be here, right? Now this error vector is like B2 minus P of 1, 2, 3, correct? Or the error vector can be either this side or on the other side, but it will be orthogonal to P of 1, 2, 3, correct? And it will be orthogonal to B1 also. So this error vector, let's call this E. E is equal to B2 minus P of 1, 2, 3, okay? Now this is going to be orthogonal to 1, 2, 3. Now what is E? What is B2 first? B2 is 1, 1, 1, right? So 1, 1, 1, okay, minus P, comma 2P, comma 3P. If you calculate this, you will get 1 minus P, 1 minus 2P, 1 minus 3P, okay? So this is your error vector. See, we can divide this by their norm later on, okay? First, for simplicity of calculation, we'll just go with this, okay? Now, what is the dot product between E and 1, 2, 3? Dot product between vector E and 1, 2, 3. This will be equal to 0. Am I right? The dot product between this vector and B1 is going to be 0. Okay? Dot product between this one and B1 is going to be 0. So what is E? E is 1 minus P, 1 minus 2P, 1 minus 3P. Okay? And B1 is 1, 2, 3. Okay? Now the dot product of these two will be 0. So when you do dot product between these two, you will get 1 minus P, okay, plus 2 times 1 minus P, 1 minus 2P, plus 3 times 1 minus 3P, correct? I'm just doing dot product. This times this times this, and this times this, and we are going to add everything together, okay? So when you add these things, you will get 1 minus P plus 2 minus 4P plus 3 minus 9P is equal to 0, okay? So this is going to be 1 plus 2, 3, 3 plus 3, 6, minus p, minus 4p, this will be minus 5p, minus 5p minus 9p is going to be minus 14p. So this is going to be 0. So what will p be? P is equal to 6 by 14. Okay, or 3 by 7. Okay, so clear about p? How to find p, you people have understood, right? So if this is p, then the projection will be this p times 1, 2, 3 is the projection, right? Projection of b onto the span of b1, correct? This p is going to be the projection. So p will be this projection, the point which is being projected is 3 by 7 times 1, 2, 3. Okay, this is going to be the point projected. So this is b1, okay, this line, and this is your b2, and this point is 3 by 7 times 1, 2, 3. Okay, the projection. And then what is your error vector? Error vector is 1 minus p, 2, 1 minus 2p, 1 minus 3p, correct? So you have to substitute 3 by 7 there. So if you substitute 3 by 7 here, you will get 1 minus 3 by 7, 1 minus 2 times 3 by 7, okay, 1 minus 3 times 3 by 7. All right. So if 1 minus 3 by 7, 1 minus 2 times 3 by 7, and 1 minus 3 times 3 by 7. Okay. So if you calculate this, you will get 7 minus 3, which is 4 by 7. Okay. 7 minus 2 3s are 6. Okay. So 7 minus 6 will be 1 by 7. Okay. And 7 minus 3 3s are 9. So 7 minus 9 is minus 2. So minus 2 by 7. Okay. So now we have to take the norm of this to find the unit vector corresponding to this. Okay. Like, is this clear? See, I'm saying all these things because I assume that you people know projections. Okay. If you don't know, kindly ask. Till now, hopefully, is it clear? It's clear, right?
Yes, sir.
Okay. If you have doubt, you can ask. So now we have to take the norm of this. Okay. That is the length. Okay. So the length is going to be the dot product of this with itself. And the square, of course, you have to take square root. Okay. So dot product between these two vectors. So this is going to be 16 by 49 plus 1 by 49 plus 4 by 49, right? So this is going to be 21 by 49. And you can cancel this. You can cancel this or you can leave it out because 49 is there. We have to take square root, right? Length of vector E will be square root of E dot product E, correct? So this is E dot product E. Now we have to take square root. So it's going to be square root of 21 by 49. Since this is length, it will be positive. So we can say 1 by 7 of root 21. Okay. So this is your length. Now we have to divide. Now we have to divide we have to multiply it with 1 by, or we can see your vector was 4 by 7, 1 by 7 minus 2 by 7. We have found out that the length, this is your vector E. The length of E is equal to root 21 by 7, right? To find the unit vector corresponding to this, you have to divide this by its norm. Okay. So this is going to be this is going to be 1 by norm times E. Okay. Now 1 by norm will be 1 by root 21 by 7. So this is going to be 7 by root 21. Okay. Now we have to multiply it with 3, scalar multiplication with E. Okay. E is 4 by 7, 1 by 7 minus 2 by 7. Okay. So if you just multiply this, you will get 4 by root 21, 1 by root 21 and minus 2 by root 21. Okay. Because the 7 with the denominator is going to get cancelled and root 21 will come to the denominator. Okay. So this is your A2, which is the second vector. the first vector will be b1 divided by its norm, right? b1 divided by its length will be a1, and for a2 this is going to be a2, correct? Clear on how to find a2? Like
Yes.
what we have to do is, b1 is there, we have to project b2 onto b1, we will get some projection. Okay, let me just repeat. We have b1 b2. Okay, now we have to project b2 onto on span of b1. Okay, span of b1. Okay, we have to project it. Now the vector which is the projected vector, you will get some projection, right? That projection will be some p times b1, right? Because the projection will be on the span only. The projection is going to be on the span, so it will be some scalar multiple of b1. Okay, so this is going to be p times some b1. Okay, p times some b1. This is going to be a projection, and now we are using the property that the error vector is b2 minus pb1, correct? This is your error vector. The property is error vector, the dot product of error vector and b1 will be 0, right? We are using this property because the error vector is going to be orthogonal to b1. Okay, so we are using this property to get 0. So from this we can get the error vector. The error vector will be your second vector, a2. The error vector will be your a2. Okay, this is what we did. Okay, so the first vector will be what is your first vector? It's going to be 1 2 3 divided 1 comma 2 comma 3 divided by its norm, right? The first vector will be b1 divided by its norm. Okay, so b1 is 1 2 3. The norm will be, you have to take dot product with itself. So if you take dot product 1 2 3 dot product with itself, this is going to be 1 square plus 2 square plus 3 square. 3 square is 9, 2 square is 4, and 1 square is 1. So 1 plus 4 5, 5 plus 9 14. Okay, and we have to take square root. Okay, so we have to take square root to get the norm, the length. Okay, so this is going to be 1 2 3. So sorry, this is going to be 1 by root 14 times 1 2 3. Okay, so this is a1, and your a2 was this vector. Okay, so which means like 4 by root 21, 1 by root 21 minus 2 by root 21, which is what we saw there, right? So this is your a2. Okay, now how will you find a3? You have got a1, you have got a2, and how will you find a3? How are you going to find a3? See, we have b3, right? We have b3. Okay, b3 is 0 2 1. Okay, b3 is 0 2 1. Now what we have to do is, we already have a1 and we have a2. Okay, we have two vectors. Now what is the span going to be? The span of this will be what? These two are orthonormal vectors. What is going to be the span of these two? What's going to be the span of these two? It will be a plane, right?
R2, yeah.
Yeah, it's going to be a plane in R3. No, it's not R2. It's a plane in R3. Okay, some plane in R3. Okay, so we have b3 now. Okay, let's say b3 is somewhere which is not there on the plane. Now we have to project it. Okay, let's say this point is the projection. I think I can draw it better. We have b3. Okay, this is your b3, and now the projection will be some point here. Okay, so this is going to be what? A linear combination of these two vectors, right? Because the span of this is this plane, and the projected vector is on this plane. Okay, so it is going to be a linear combination of a1 and a2. Okay, so a linear combination means, let us call this, once again, so this point is there on the span of A1 and A2. Okay, so it's going to be a linear combination of A1 and A2. So we can represent this point as some x times A1, okay, plus some y times A2, right? X and y are some scalars, okay? A1 is your first vector, okay, this is your A1, all right, and this is your A2, okay? Some linear combination of these two will be this point. Clear? Will be this vector. Am I right? Some linear combination of these two is going to be this vector. So we can represent this as x times A1 plus y times A2. Okay. Now what do we know? Where will the error vector be then? Then what is going to be the error vector? It will be perpendicular to this plane, correct? It is going to be perpendicular to this plane. Am I right? The error vector. Okay, how will we get the error vector? The error vector is equal to B3, okay, minus xa1 plus ya2, right? So this is going to be your error vector. Now this error vector will be your A3, right? Because A1, A2 and A3 have to be orthogonal to each other. So only the error vector we know it's the orthogonal vector. It's in a way corresponding to this B3. So this will be your A3, okay? The error vector. Now let me not use this 1 by root 14 and all, okay? See, this vector is, see, A1 is 1 by root 14 times 1, 2, 3, right? And A2 is 1 by root 21 times 1 by root 21 times 4, 1, 2, right?
4, 1
4, 1
minus 2.
minus 2, okay? 4, 1 minus 2. Now what do we mean? What do we mean by saying this is going to be orthogonal to this plane? It will be orthogonal. Your error vector is going to be orthogonal to A1. It is also going to be orthogonal to A2. Okay. So E times A1, E dot product with A1 is going to be 0. E dot product with A2 is also going to be 0, right? So we are going to use this property to find the unknown x and y. If we know this unknown x and y, then we can find this part. We know what B3 is. We can subtract these two to get the error vector. Okay, this is what we are going to do. But for doing this, I'm not going to use this 1 by root 14, 1 by root 21. Okay.
So
If I don't use, sorry.
yeah, I just probably I'm not understanding the projections, but last time when you projected V3, you made it, it was a scalar multiple of vector A, and right now when you're projecting, it's a point, right? So when does it actually project into a point, and when does it project into a line?
No, no, no. See, it projects. See, it is going to be, it's going to project on a subspace. Okay. It's going to project on a subspace, and the vector which is the projection. Okay. Like let's say on this line. Okay, let me not take this vector. Let's say we take this vector. Now the projection is going to be somewhere here. So this line is a subspace, and this vector is your projection. Okay. So you project onto a subspace. Okay. And what is the subspace? It is the span of, see, if it is a line, it's going to be a span of one vector. Okay. If it's a plane, it's going to be a span of two vectors. Okay. So that is what we did. So the reason why I took a line for finding A2 was because we wanted to project B2 onto the span of B1. Okay. So B1 is going to span a line, right? It's not going to span more than that. So you have B2 somewhere. So the projection will be on this line. Now we know that this line is some scale. This line is the span of this vector, right?
Yes.
So this is going to be some scalar multiple of B1. That's why I took some P times B1. Now this plane Now this plane is spanned by both A1 and A2. Okay. A1 and A2 are just the unit vectors. Just the unit vectors of those vectors. Okay. So A2 was obtained by getting the error vector.
Sir,
Yeah.
sir, I'm not able to understand what is this error vector.
See this error vector, like
So can you
Can you
explain
explain the logic?
projections? Yeah.
yeah. Okay, fine. I'll explain
Sir,
first.
if possible, like I'm not able to understand with this. Can
Okay.
you simulate in the GeoGebra?
I think in GeoGebra, like first I'll just draw it here. Okay. Okay, this is your x-axis, y-axis, and z-axis. Okay. You want me to explain the projections, right?
Yeah,
Yes.
like the logic of
Yeah.
error
I'll
vector.
explain. Okay. Let's say there's a plane. Okay. Let's say there's a plane. All right. And this is your plane. I think I need not share this. It's not going good. Just see that this is a plane. Okay. Now we'll take one vector. Okay. Let's take some vector which is not there on this plane. Let's take some vector which is not there on this plane first. If it is there, then it's fine. It's easy. Now this vector, what does projection mean? Let's say you're standing. Okay. Let's say a ball is hanging here and there's a wall behind it. Now straight to this, if let's say the room is fully dark. Now let's say you have a torchlight. Okay. And you switch on your torchlight facing the wall. Okay. Now this ball will form a shadow here, right? Every other part will be bright except one part, right? So that point is kind of the projection. Okay.
So the smallest ray, the smallest path will be
Yeah.
the projection,
Yeah.
right?
Of course, the torch has to be. Of course, when you the torch should be placed here. Okay. It should be placed like this. Okay. If it is placed like it should be placed like this. Okay. So the torch light, when you switch on, the entire room is dark. Now, except this point will form, this ball will form a shadow here. Okay. Every other point will be bright except this point. So this is what projection in some sense means like. Okay. So we want to find this point. All right. So first, the basic idea of what projection is clear, right? First.
That is fine. So sir has explained in the lectures also, but I don't understand what is this error vector.
Yeah. I'll come to that. Now let's say we have. Now this is a one-dimensional space, right? One-dimensional subspace. Okay. Let's say we have some vector here. Okay. Now let's say this is the basis for this vector. Let this be basis b1. Okay. Let this be b1 and let this be vector b2. Now if you project it here, what does projection mean? It is going to be like here, it's going to be 90 degrees here. Am I right?
Yeah.
Okay. So now this point or this vector, okay, this vector is going to be a linear combination of this b1. In this case, it's going to be a scalar multiple. True, right? It's going to be a scalar multiple of b1. Okay. Now what is b1? Okay, let's forget about the question. Now the scalar multiple of b1 will be some p times b1. True. P is some scalar. Okay. P is some scalar and b is your vector. Okay. So this is
PB1 will be on the same
yeah.
line.
This is your projection. Exactly. It's going to be on this line. Okay. And this point is the projection of b2 here. Okay.
Okay.
Okay. So till now, if this is clear, it's fine. Okay. Now the third thing, see when you add two vectors, it will the point will be like the parallel the opposite vertex of like a parallelogram kind of thing, right? When you add two vectors, where is it going to be? It is going to be it's going to be the other vertex of the parallelogram, right? This one everybody knows, right? In week 1 we saw, right? When we add two vectors, the resultant vector will be here. right?
Yes.
Okay. Now if you subtract these two vectors, this vector, okay, PB1, B2 minus PB1, okay, where will this be? If you add these two, it's going to be kind of some parallelogram kind of thing, right?
Yeah, it will be perpendicular
Okay.
to the line.
Yeah, it's going to be perpendicular. Before that, maybe we can do one more thing. You have to add, let's say some vector is E, okay? You add it with PB. Let's say this is vector E, okay? This is vector E. If you add it with PB1, what is going to be the resultant vector?
B2.
B2, right? Because through parallelogram, that visualization, you can see that it's going to be B2, okay? So E times E plus PB1 is going to be B2, okay? Then E will be B2 minus PB1, okay? True? E is going to be B2 minus PB1, okay? Now you notice one thing. This is a parallelogram, right? This is a parallelogram. Now this is going to be with 90 degrees, correct? It's going to be 90 degrees everywhere. So this is like a rectangle kind of thing, right? Now if this is rectangle, then the length of this is going to be equal to the length of this, right?
Yes.
Okay. Till now, is everything clear?
Yes.
Right?
Yes.
Yeah. Okay. The length of this is going to be the same as the length of this one. Okay. Because this is 90 degrees. Okay. In even if it is not the case, in parallelogram, the opposite sides are going to be equal, right? The length. Now, what is the distance between these two? B2 and PB1. Distance between this point and this point is going to be this green line here, right?
Yes.
Okay. So similarly, so that is the distance between B2 and PB1 is going to be this length. Okay. Now why we call this error is because like this is the distance, right? This is what makes difference between these two.
So then why did you draw a vector to the
No,
opposite
like
side?
it's a vector, okay? It's a vector, but I'm just purely talking about this point here.
No, the one
Which blue one? Here.
to the opposite side. Is it just an arrow or
This one. No, I'm not getting. This is just
no?
just see
No,
the locations.
no.
See this. No, this
Towards
one,
PB1,
this
you
one,
have drawn a vector, right?
this one,
Yeah, no,
this one, this one, huh?
um, no, to the right side. Um,
Yeah, that
No,
is parallel to that is on the line. That is what was my question. It is
which one? Yeah, this is on the line. This
projecting
is
out.
going to be on.
Yeah, you've shown it as though it is coming out of the line, right? So,
Is it?
no,
Okay,
that
let me
is
draw it again. Okay,
PB1 is the scalar
let
of.
me draw it again. Once again, let me draw it again. Okay, so this is your span of B1. Okay, this is your origin. This is B1. This is span of B1. Okay, now this vector is B2. Okay, now the projection of this is going to be here. Correct?
Yeah.
Okay, this is going to be a projection. Now this will be 90 degrees. Okay, this is going to be 90 degrees. Now this you can refer to this point as some p times b1. Okay, because a scalar multiple of b1 is going to be this one. Okay.
So
Now,
this just a clarification that a vector is neither array and neither a line segment, right? Because it has a direction also,
yeah, it has a
but it
direction. I'm
has
just
a
talking.
magnitude also.
Yeah. It has direction, so that's why we represent it with this arrow. Okay, just for simplicity, I was saying. Okay. So now this blue arrow, right? This is your PB1.
Yeah.
Clear? This arrow right from here to here. Okay. Now that using that parallelogram idea, I told that E is going to be here. Correct? E is going to be here. Okay. Now the reason why this is called as error vector is the length of this vector is same as the length of this line. Okay, this is not a vector. Okay, this is not a vector. This one here, which we are representing it with some dotted lines, it's not a vector. It's not a vector. But if you look at this, these two are parallel, and if the length of this is going to be same as the length of this one, correct?
Yes.
Okay. Now in some way, this is the distance between PB1 and B2 is represented by this vector. Okay. So that's why it is called as error vector. Like by error, they mean they are the reason why these two are not the same. Okay. The reason why these two are not the same is because of this error. Okay. The reason why this B2 and PB1 are not the same is because of this error. Okay. The error is the distance between those two vectors. Okay.
Okay.
Clear? Till now it's clear?
Yes.
Okay. For others? Now since this is going to be 90 degrees, this is 90 degrees, right? So this vector and this B1 is going to be orthogonal, correct? Then this is 90 degrees.
Yes.
The error vector times B1 is going to be 0. Okay, that is the dot product. Okay, this is dot product. Okay. So what is error vector? B2 minus PB1, right? B2 minus PB1. Okay. So this is your error vector. Now you do dot product with B1, you will get 0. Okay. Fine. Now we want to find P. Okay. So first, if you do dot product, what will you get? B1, B2 minus P1, B2 minus P times norm square of norm square of B1, right? See, B1 dot product with B2 will be B1 dot product B2. P is going to be some scalar. Okay. So B1 dot product with B1 is going to be norm square of B1 and multiplied by P. Correct? Right? So now we have to find P. Now we know this is equal to 0. So you take this to the other side. Okay. So B1 dot product B2 is going to be P times norm of B1 square. Okay. So you take this back here. So this is going to be P is equal to B1 B2 by norm of B1, the square of norm. Okay. You can call it as square of norm, or you can simply leave it as dot product of B1. Okay, B1 dot product B1. You can leave it as it is. Okay, this is P. Understood? Is it clear, everybody?
Yes, sir.
Okay, so this is projection onto a line. Okay. Now we have to project it. Now for a vector, we have to project it on a plane. Okay. So for plane, again, let's say this is the plane. Okay. Now there are two bases for this plane. Okay. One is B1, other one is B2. Okay. Let's say there are two bases. Okay. Now let's say this vector B3 is not on this plane. Now where will the projection be? The projection is going to be over here, right? Somewhere over here. Correct?
Yes, sir.
Am I right? Now this is on the plane, right? This projection is on the plane. Okay. Now since this is on the plane, this can be obtained as a linear combination of B1 and B2. Correct?
Yeah.
Okay. So this can be obtained as a linear one second, let me just plug in my charger. Just a second. Yeah, really sorry. So this projection can be obtained as a linear combination of B1 and B2. Okay. So we will write this as some x times B1, okay, plus some y times B2. Okay. This is some x times B1 plus some y times B2. Correct? So here what is going to be the error vector then? Then what is going to be the error vector? This will again be perpendicular to this plane. Correct? The error vector.
Yes.
Okay. The error vector will be perpendicular to this plane. Because here, let me just draw this dotted lines again. So this dotted lines, this is of 90 degrees, right? The projection will form 90 degrees here. So from this and using that parallelogram idea, we can say the error vector is also going to be somewhat like this, right? This is going to be our error vector and this will be 90 degrees to the plane. Okay. All right. So this is error vector, but this time the error vector is, now this time what will be this error vector? Error vector will be like B3. Remember last time we did B2 minus its projection, right? B2 minus its projection. Now we will do B3 minus its projection. So B3 minus XB1 plus YB2. Okay. So this is going to be our error vector. Clear?
Sir, in the previous case,
Yeah,
can you go to the previous slide?
this one.
What if the B1 is towards the right of the projection? Then
Here.
can we take, yeah,
Yeah, then also you
yeah.
divide it by something and you will get it here, right? Let's say this is
Mhm.
2 comma 0 and let's say this is 1 comma 0. You multiply this by 1 by 2 times 2 comma 0, it's going to be 1 comma 0, right? Every vector on this plane is some scalar multiple of the B1, right?
I'm saying then can we take the projection as the error vector?
This vector.
If it is, if
Yeah,
the
see what
vector
you're asking
B1
is,
is towards the right, right? Yeah.
if this is B1, can we say that this is the projection? This is
Yeah,
what you're
and
asking.
can we say this dotted lines is the error
This one.
vector? If the
Yeah, yeah,
vector
yeah.
B1
Yeah,
is
the
correct.
dotted line is with respect to PB1. Okay. Yeah, you can see. Still, the
Okay.
projection is going to be the same in this vector, right?
Okay. Since in this case it's not a vector, we can't say it is a
No, this is a
vector.
vector. Which one are you talking about?
In,
PB1
in,
or
the, in this case, when B1
this
is
dotted
towards the
line is,
left,
see,
yeah,
this dotted line is not a vector. Okay.
yeah, yeah.
This E is a vector, PB1 is a vector, B2 is a vector, and B1, whether here or here, it's going to be a vector. Okay.
Okay. When B1 is towards the right, right,
Here.
on the same line, then
Ah,
we can take this dotted line as a vector, right?
the corresponding the the vector corresponding to this dotted line can be taken as the thing. See, like
Okay.
I
When
think you're asking like B1 is here, B2 is here, PB1 is here, right? Now you're
yeah.
asking, can you take this as what?
Um, uh,
This is not a vector, okay? This is not a vector.
okay.
This is just
Okay.
this is just to show that it's 90 degrees. Okay.
Okay.
Okay. So your error vector can be obtained as B3 minus x times B1 plus y times B2. Okay. Now, if you think of this, you can also represent this as a matrix, right? So this B1, you can take it as a column vector. B2 also can be taken as a column vector. Okay. Times xy. Okay. This is also possible, right? For this. Right. This is also possible. We can do it like that also, but just for simplicity, I think we can leave it at this point. Maybe if there are too many vectors and too many, like, it is some r power some 5 or 6, then I think you need plane matrices. But right now this should be enough, right? So this is your error vector. Now error vector is going to be orthogonal to what? Now the error vector is going to be orthogonal to what? Sorry.
To the plane.
Once again. Sorry guys. So it is going to be orthogonal to what? Error vector is going to be orthogonal to
The plane.
to this plane, right? So this plane, so you can say that this plane is going to, this error vector dot product with b1 will be 0. This error vector dot product b2 will also be 0, right? So if you use this, you will get two equations, okay? So yeah, you will get two equations, x and y are unknowns, okay? So with these two equations, you can find x and y, okay? Clear? Clear? If this is clear, I think we can go to the question back. Fine?
Yes.
Yeah. Really sorry, by mistake I clicked on something else. Yeah. So we can go to the question. Okay. Here, so with like is A2 fine or should I do A2 again? Is A2 fine? Is A2?
Yeah, we can go to the next if everyone is okay.
Yeah, if everyone is okay, we can go to A2. Okay, fine. So I think this is not needed. So your A1 was equal to 1 by root 14 of 1, 2, 3. Okay. Now your A2 is 1 by root 21 of 4, 1 minus 2. Okay. So this option was correct. So 4, 1 minus 2. Okay. Now we need A3. So now this A3 is going to be the error vector. Okay. This A3 is going to be the error vector. Now what is the error vector? This error vector will be B3 minus some x times A1. Sorry. Error vector will be B3 minus x times A1 minus x times y times A2. Correct? So this is going to be our error vector. Okay. Now this A1 you need not take 1 by root 14 and all, because let's say these two vectors are there. If this is orthogonal to this vector, then it's also orthogonal to this vector, right? If this vector is orthogonal to this vector, it's also going to be orthogonal to this vector. Correct? So we can take out 1 by root 14, 1 by root 21 and all. At the end, we can just find the norm and we can get the unit vector form of this. Okay. So let us not take A1. Let us have, let's have A1 dash, which is equal to 1, 2, 3. And let us have A2 dash, which is equal to 4, 1 minus 2. Okay. Hope everybody is okay with what I told right now, right?
Yes.
Yeah. This is for simplicity of calculation. So E is equal to what is B3? 0, 2, 1, right? B3 is 0, 2, 1. Okay. Minus x times A is A1 dash. Okay. We'll take A1 dash and A2 dash. So A1 dash is 1, 2, 3. Minus y times A2 dash is 4, 1 minus 2. Okay. 4, 1 minus 2. So this is your error vector. So this is going to be equal to minus x minus 4y. Okay. 2 minus 2x minus y Okay, 1 minus 3x plus 2y. Okay, minus 2 minus y is going to be plus 2y. So this is your error vector. Now we are going to use this property. Error vector is orthogonal to a1 dash. Error vector is orthogonal to a2 dash. Okay, with this property we are going to get two equations. With these two equations we are going to solve these two unknowns x and y. Clear? So once we get the error vector, we have got the third orthonormal vector. Okay, let's say, okay, let me write a3 is error vector divided by its norm. Okay, fine. So first thing is it is orthogonal to a1, right? What is this? This is minus x minus 4y, minus x minus 4y. Okay, 2 minus 2x minus y, 2 minus 2x minus y. Okay, then 1 minus 3x plus 2. Okay, 1 minus 3x plus 2. Okay, now this, the dot product with 1, 2, 3. Okay, this is a1 dash. This is going to be equal to 0. Okay, so this, if this is equal to 0, then after taking dot product we'll get minus x minus 4y, this multiplied by 1. Okay, then this multiplied by 2. Okay, so plus 2 2s are 4. Okay, so 4 minus 4x minus 2y. Okay, then this times this, so plus 1 3s are 3, minus 3 into 3 minus 9. Okay, minus 9x, 2 3s are 6, plus 6y. So this is equal to 0. Okay, so let us add 4 and 3. Okay, 4 plus 3 is 7, minus x minus 4x minus 5x, minus 5x minus 9x is minus 14x. Okay, so minus 14x minus 4y minus 2y minus 6y plus 6y is 0y. Okay, so plus 0y is equal to 0. So 7 minus 14x is 0. X is going to be 7 by 14, which is equal to 1 by 2.
Good.
Yeah,
How did you get 3?
where this
I
one.
mean, 3 minus 9x plus 6y will be 3 times of.
No, 1. This is 1. Okay,
Oh, okay.
I think I have not written it properly. Yeah, this is 1. Okay, fine. So hope everybody understood on how we get x, right? So this is x. X is 1 by 2. Okay. Now if you cannot substitute it back here itself because you can see 0y, right? However, you're going to add, you're going to get 0y, so you can't find y from here. So we will use the other equation, right? The other equation is error vector, the dot product with a2 dash is going to be 0 again. Okay, same. So minus x minus 4y. Okay, then 2 minus 2x minus y, 2 minus 2x minus y. Okay, then 1 minus 3x plus 2y, 1 minus 2x plus 3y. Okay, if I'm going wrong somewhere with calculation, please let me know. Okay, 1 minus 3x plus 2y. The dot product with the second vector was 4 1 and minus 2.
It
Okay.
is 1 minus 3x plus 2y.
Okay, yeah, thank you so much. 1 minus 3x plus 2y. Okay, so the dot product of this with 4 1 minus 2 is going to be 0. Okay, so this times 4 will be minus 4x minus 16y. Okay, next the dot product of this with 1 is going to be 2 minus 2x minus y. Okay, plus the dot product of this with minus 2 is, okay, this is 1 minus 2, so it's going to be minus 2. Okay, so this is minus 2, minus 3x minus 2 is going to be plus 6x, 2y minus 2 is going to be minus 4y. Okay, this should be equal to 0. Clear? Now minus 4x minus 2x minus 6x plus 6x is 0x. Okay, minus 16y minus y minus 17y minus 4y minus 21y. Okay, minus 21y to minus 2. Okay, so 0. this is equal to 0. So minus 21y is equal to 0. So y will be 0. Okay. So we have got x and y. Okay. Now your error vector is, this is your error vector, which is, let me write that again. Error vector is minus x minus 4y, 2 minus 2x minus y. Okay. 2 minus 2x minus y. Then 1 minus 3x plus 2y. Plus 2y. Okay. Now we have to substitute a, x and y. X is equal to 1 by 2. Y is equal to 0. Substitute it here. You will get minus 1 by 2. Okay. 2 minus 2 times 1 by 2. 1 minus 3 times 1 by 2. Okay. So this is going to be minus 1 by 2. 2 minus 1. Okay. 2 and 2 cancel. So 1. 2 minus 1 is 1. And 1 minus 3 by 2 is going to be minus 1 by 2. Okay. Now I think you can write this as 1 by 2 of minus 1, 1, minus 1. Okay. Now we can take out this 1 by 2, okay, for calculation of norm. Because let's say the norm of,
How can you take the y term is only 1? No? So
see, like what I'm saying is 1 by, error vector is this one, right? Error vector is 1 by 2 of minus 1, 1, minus 1, right?
So if you take 1 by 2 common, it will be 2 right in middle.
See, I'm taking 1 by 2 outside. Okay. Error vector
Yeah,
is
then
1 by 2 times minus 1, 1, minus 1. Is it
yeah,
clear?
then the second element.
second.
Sorry.
No, I'm not getting what you're asking.
The second element should be 2, right? If you take 1 by 2 as common.
Oh, yeah. I'm sorry. Okay. Fine. Understood. Okay. Fine. Now this is your error vector. Okay. Now we have to find E by the length of E. Okay. Now this is, to find this, either we can find it with 1 by 2 or
So
let's find, yeah.
it's 1 only. After taking common, you will get 2 inside.
See, okay, this
It's
is
2
okay.
minus
Yeah.
1, which is 1.
Yeah. Okay, fine. I'm sorry. Okay. No more errors here, right? Except the error vector, no more error, right?
So I'm saying it's actually 1 itself, 1 only in the middle element. After
Okay,
taking
1
1
second,
by
1
2
second, please.
common,
2, yeah, let me recalculate, okay?
Yeah.
See, this is 2 minus 1 by 2 times 1 by 2, okay? So 2 and 2 cancel. This will be 2 minus 1. This will be 1. Okay. So this is going to be 1. So if we take common outside, this is going to be 2. Now it's clear, right?
Yeah, fine.
Yeah, hopefully no more errors except the error vector. Yeah. Now to find A3, we need E by norm of E. Okay. So for E, you can use 1 by 2. Okay. You have 1 by 2. Either you can take dot product with this and then divide it. Those things you can do. Or you can do this. Okay. Let's have some vector Q which is equal to minus 1, 2, 1. I'm just taking this part. Okay. Now I am saying A3 is also equal to Q by norm of Q. Correct? Do you all agree with this? I'm saying A3, we saw that A3 should be equal to E by norm of E, right?
Yes.
Now what I did was, I took Q outside. I took Q. Q is minus 1, 2, 1. I took this here. Okay. Now Q by norm of Q can also be A3. Do you all agree?
Yes.
See, okay, for those who don't understand, the reason is, like they said, this is, let's say this is 1, 0, okay? Now this is 2, let's say this is 3, 0, okay? And this is like 5, 0. Now, what is 5, 0 divided by the norm of 5, 0? It is going to be unit vector on this line, right? So that will be 1, 0. And similarly, 3 by 3 comma 0 divided by the norm of 3 comma 0 is also going to be 1 comma 0. Okay, because this is unit vector 1 0. Okay, so which is why I'm just taking this part outside. The scalar, you can take it and you can multiply and take square root, those things are fine, but without that also we can do. Okay, so this is going to be, the norm is going to be, the norm of Q is going to be dot product of -1 to 1 -1 to 1. Okay, so this is going to be square root of -1 square, which is 1, plus 2 square 4, plus 1 -1 square 1. This is -1. Okay, 1. So this is going to be square root of 6. Okay, so you can take A3 is equal to A3, as we told, it's going to be Q by norm of Q. So this is going to be 1 by root 6 times -1 to 1. Okay, clear? Hope you all understood, right? Let us see whether this is correct or not. 1 by root 6 minus 1 to 1. Yeah, this first option itself is correct. Okay, let's just check these two. Yeah, so these two are correct. Hope you all understood how to do Gram-Schmidt process, right? You will have 3 vectors. Okay, 3 vectors for the basis for R3. You take the first vector, that is going to be the first vector. Okay, and of course in its unit vector form. Then the second vector is going to be, let me just explain the procedure as a summary. Okay, you have 3 vectors b1, b2, b3. Now you need 3 orthonormal vectors as the basis. Okay, you first vector is a1, this will be b1 divided by the norm of b1. Okay, now second one for a2, it is going to be, you first project b2 onto b1. Okay, you project it. Okay, project, you will get some p times b1 as the projection. Find E is equal to b2 minus pb1. Solve the equations, and E2 is going to be, let's say this is E2. Okay, this is, let's say this error vector is E2. So A2 is going to be E2 divided by the norm of E2. Okay, and similarly A3, take B3, project it onto the span of B1 and B2. Sorry, I'm sorry. Project it onto the span of A1 and A2. Okay, A1 and A2. A1, A2. Span of these two vectors. Okay, project it onto these two. The projection will be some x times a1 plus some y times a2. Okay, now you can find error vector e3, which is equal to b3 minus x times a1 minus some y times a2. Clear? So this is e3. Okay, now a3 is equal to e3 divided by the norm of e3. This is usual length. Okay, so now your a1, a2 and a3, these 3 are your orthonormal sets, basis sets. Okay, hope everybody understood this Gram-Schmidt process, right? If you have understood, we can go to the next question. Okay, so then this is how to find orthonormal basis. See, the fourth and fifth are going to be similar. Okay, again you have to do the fourth. Okay, let me come to those. The third is v1 is equal to 1 0 1 1. Okay, I'm going to the next question. Okay, if you have any doubt in the previous question, please ask me. Otherwise, we can go to the next question. Okay, fine. Now we have v1. V1 is 1 0 1 1. Okay, 1 0 1, and v2 is 0 1 1 1. Okay, 0 1 1 1. Okay, now what we need is, what the question is saying is, there's some vector v3. This is some v1 plus a times v1. Okay, v3 is equal to v1, sorry, v2 plus some a times v1. Okay, a is some scalar. Okay, now v1 and v3 are orthogonal. They're saying this v3 is orthogonal to V1. Okay. So with these informations, what we have to do is we have to find A. Okay. We have to find A with these informations. So how will we start? How will we start? Anant, Bhumika, Ravesh, anybody? How will we start? We have V3 given as this. V1 and V2 are vectors given here. Okay. We have V3 which is equal to V2 plus AV1. And this V3 is orthogonal to V1. Okay. So how will we find A now? Okay. First let's find V3. Okay. V3 is V2 plus AV1. Okay. So this is going to be 0, 1, 1, 1 plus some A times 1, 0, 1, 1. Okay. So this will be equal to A 1 plus A times 0, which is 1, 1 plus A, okay, and 1 plus A, okay, 0 A, yeah, hope this is correct, okay. Now this is V3. Now we need to find A. The information which we have is V is orthogonal to V1. Sorry, V3 is orthogonal to V1, which means the dot product of V3 times the dot product of V1 will be 0, okay. So the dot product of V3 is like V3 dot product V1 is A 1 1 plus A and then 1 plus A. Okay. The dot product of this with 1 0 1 1. Okay. So this will be equal to A times 1, which is A, plus 1 times 0, which is 0. 1 plus A times 1 is 1 plus A, and then 1 plus A times 1 is 1 plus A. Okay. So this is going to be A 3A. Okay. And 1 plus 1 2. Okay. We know that this is equal to 0, correct? We know that 3A plus 2 is equal to 0 because dot product of V3 and V1 is going to be 0. Okay. So from this we can see A is minus 2 by 3. Okay. So minus 2 by 3 is here. Okay. Yeah. Understood. This third question, I think it was simple, right? Yeah. Now the fourth question is like W is a subspace of the inner product space R4. Okay. With respect to dot product. Okay. And V1, V2, V3 is the ordered basis of W. Okay, what they are saying is W3 is a subspace, okay, in R4. Now this R4 is an inner product space. Okay. Now V1, V2, V3 is an ordered basis of W. Okay. They have given V1, V2, V3. Now which of these is the orthonormal basis for W? Okay. So how will you go about this? How will you go about this?
So can you show the question?
Like, okay, like the question is just about informations. The thing is they have given 3 vectors, okay? 3 vectors which is basis for W. V1, V2, V3 is an ordered basis for W. From this we want orthonormal basis. That is we have to do Gram-Schmidt process. Okay. And we have to see which option is correct. Okay. Again the same thing, but now it is an R power 4. However, we have only 3 basis vectors, right? However, we have 3 basis vectors, so it is just going to be the same thing. You take this as V1, project V2 onto the span of V1. Okay, this V1 will, if I can say, a line in R power 4. Okay, we don't know how R power 4 will look like, but it's going to be some, let's say it's some line in R power 4. Okay, V1 will span some line in R power 4. You project V2 onto V1, you will get a projection, and you take error vector. You have to find those. Should I do this question? Because like we have to do 8.5 also. If you want, I can do this question. It's up to you. This for you only. Okay. Should I do Gram-Schmidt process again? Hello.
Can can go to the next.
Okay. Others, if everybody is clear, I can go. Okay. Otherwise, I can do this again. No issues. I just want others to also say something. Okay. One of them I've told, please move on. Fine. See, if somebody wants, please interrupt. Okay. Otherwise, I'll assume that we can move on. Because this is going to be same gram scheme process, but now it's in R power 4. That's all. Okay. Fine. Now the fifth question. There's a vector. Okay. There's a vector A. They have given some vector A. Now they are saying that in R3, W is a subspace. Okay, W is a subspace in R3. Now look at the set W. The set W is set of all the vectors of the form x comma y comma z such that the inner product of this with vector A. Okay, with vector A, the inner product of this vector along with A is 0. Okay, and they have given that the inner product is the dot product here. Okay, the inner product is the dot product here. So what they are essentially asking is, they are asking the set of all the W3 is what? What is W3? W3 is set of all the vectors, okay, for which the dot product with vector A is going to be 0. Right? So in R3, if there is a vector, for every vector there is going to be a plane which is orthogonal to this plane, right? Sorry, to this vector, right? In R3, okay, let's say this is some vector, okay? Let's say this is your vector A. Now there's going to be an entire plane which is orthogonal to this vector, right? Every vector in this plane is going to be orthogonal to A. Am I right? This is true for every vector, correct?
Yes.
So essentially, what is set W? Set W is some subspace, right? Is some two-dimensional subspace, right? Now this is what null space also means, right? If you consider this as a row as a matrix, the matrix will be like 2 by 3, 1 by 3, and sorry, 2 by 3, 2 by 3, and 1 by 3, right? So this is the vector. Okay, now if you consider this as a matrix, let me remove the commas. Now the null space of this is going to be a plane, correct? The null space of this matrix is going to be a plane. Am I right? The null space is orthogonal to the if let's say this is the vector, the null space of this vector is going to be orthogonal to this, correct? Everybody knows this, right? The null space is going to be orthogonal to this vector, correct? The null space, this is the vector, this plane is the null space of this vector. Okay, so this will be orthogonal to this vector A, correct? So how will you find null space? This is a matrix, right? So what can you do? You can convert it into reduced row echelon form. Multiply this matrix 3, you multiply the first row, there's only one row, so you can multiply this by 3 by 2. Okay, there's only one row, of course. So the first one will be 1, second one will be 1, third one will be 1 by 2, right? 3 and 3 cancel and 1 by 2. Okay, so this is your reduced row echelon form. That is 1, 1, 1 by 2. This is your reduced row echelon form. Now you can also augment 0 with this to find the null space. You can augment 0 with this to find the null space. So if you augment 0 and you convert this to equation, what will you get? X plus y plus z, z by 2 is equal to 0. Okay. So from this you can see x is equal to minus y minus z by 2, correct? Now you can see these two are independent variables, right? The second and third column do not have a leading entry. Only the first column has a leading entry. These two columns do not have leading entries. So the second unknown variable, which is y, and the third unknown variable, which is z, they are independent variables. Okay. So what is the solution of null space? It's going to be minus y minus z by 2. I'm sorry, this is 2. Minus y minus z by 2. Okay. y, and z. This is going to be the null space, right? This is how the set of all vectors of this form is going to be the null space. Now from this you can find a basis, right? The basis is going to be -1, 1, 0 and -1/2, 0, 1. Correct? Am I right? That's the same thing which we are doing from week 5. Any doubt? So these two can be the basis. You can check for independence also. These two are going to be the basis. And from this, see which vectors are of this form. Okay? See which vectors are of this form. Is 1, 0, 2 of this form? Like what I'm saying is, if this is the basis for null space, okay? These two are the basis for null space. Now every vector in this null space is going to be of this form. Every vector in the null space is going to be of the form y minus z/2. Okay? It's going to be of the form y minus z/2 minus y minus z/2 yz. It's going to be of this form. Now you take 1, 0, 2. You take 1, 0, 2. And what is y minus z? You know y is equal to 0. Z is equal to 2. So minus y minus z/2 should be equal to -0 minus 2/2, which is should be 0 minus 1, right? But this is 1 here. So this is clearly not in the null space, correct? This is clearly not in the null space. So you can say this option is wrong. You can take the second option, 1, 0, minus 2. Equate this to 1, 0, minus 2. Okay. You can see y is 0, z is minus 2. So minus y minus z/2, which is -0 minus of -2/2. Okay. So minus into minus will be plus, 2/2 will be 1. So it is going to be 1. The first one should be 1, right? And it is 1 here. So this can be in the null space. And look at the second vector, 0, 1, minus 2. Okay. 0, 1, minus 2. Fine. So what is 0, 1, minus 2? Again, now y is 1, z is minus 2. Okay. So minus y minus z will be -1 minus of -2/2. Okay. So this is going to be -1 minus into minus plus. So it is going to be +2/2, which is 1. So -1 plus 1 is 0. Okay. So this is also in null space. And you can also verify that these two are linearly independent. Okay. The checking for linear independence of these two, I think it shouldn't be very difficult. Okay. So this can be thought of as a basis. Now notice the third vector. You multiply the first vector by -1, you will get this vector. You multiply this vector by -1, you will get this vector. Okay. So these two can also be the basis, right? Am I right? These two can also be the basis. Okay.
Yes.
Now notice the fourth one. We already saw 1, 0, 2 cannot be orthogonal to A, right? Because it is not of this form. It is not there in the null space. You can just multiply and see 1, 0, 2. You can just take dot product with this vector A. Okay. 1 times 2/3 plus 2 times 1/3. So what will you get? 2/3 plus 2/3. Okay. You can just multiply and see it won't be 0. Sorry. You can just take the dot product and see it won't be 0. So if this option is wrong, this option is also definitely wrong. Okay. So these two options are correct. Okay. Or if you don't have time, you can just take the options, take the vectors, just take dot product with this vector and see. And check for linear independence. That's also another way to. Clear? If there's any doubt, you can ask. Otherwise, we can go to the next activity. Fine.
Sir, we can even check with the linear combination of the spaces, right?
No, like your linear combination of these two. These vectors.
Yeah.
Okay. You want the linear combination to be like orthogonal to A, right?
Yeah.
Yeah, that is one way, like, but just make sure both are not zero, right? Just make sure both are contributing something. And of course, you have to check for linear independence. Check for linear independence and just make sure both the scalars, while you take linear combination, make sure the scalars are not zero. Because maybe one vector is orthogonal, but the other vector is not orthogonal. That is also possible, right? So just check for that also. Okay. Yeah. Fine. Okay, so then we can go to activity 8.5. Okay, check for linear independence also in the last. Okay. Yeah. So we have 7 questions here. Okay. Are you all okay with orthogonal transformations and those things?
So you have to explain.
Okay, fine. Okay.
So,
Yeah.
can you explain the properties of the transformation?
Orthogonal transformation.
Yeah.
Yeah, 1 second. Yeah. See, the thing is, basically the definition of orthogonal transformation is, first thing, it's a linear transformation from the vector space to itself. Okay. First thing, okay, let me take, sorry. One second. Yeah. So first thing is about so first thing about orthogonal transformations is like the domain and codomain are V. Okay, some vector space. The domain and codomain are the same vector space. Okay. Now T will be an orthogonal transformation. Okay. If the inner product of TV, okay, you send some vector V inside, okay, you're going to get some output. That is T of V. Inner product of T of V, they have given TV, okay. There they have given TV, maybe you can take that also, okay. TV, comma TU. U is also some other input, and T of U is going to be the output, okay. The inner product of this, if this is equal to inner product of VU, okay. U and V are inputs. These two are inputs, okay. And the outputs are TV1 and TV2. The inner product between the inner inputs, if it is equal to the inner product with the outputs for all the vectors in V, okay, for all the vectors in the vector space V, then we say this is an orthogonal transformation. So the basic thing is clear, right? There's a vector space for domain, the same vector space is for the codomain. You're going to have a linear transformation T from domain to codomain. Basically both are same vector spaces. Okay. Now the input is V and U. Okay. Some V and U from this vector space. The inner product between V and U, if it is equal to the inner product with their corresponding outputs. The V is the input, corresponding output is TV. U is the output, corresponding output is TU. Okay. If you like, if this inner product is equal to this inner product for all such vectors V and U in the vector space in the domain, okay, then we say this is orthogonal transformation. Clear?
Yes.
Okay, this is the basic. But here what they have given is, this is the basic definition. So there will be a linear transformation. The thing is, there will be a linear transformation given to you. Okay. What you have to do is you have to find T of x1, y1, T of x2, y2. You will get some vectors. You have to take inner product between those two vectors, and you have to take the inner product with the input. See if LHS is equal to RHS. Okay. For all the vectors. Okay. For all the vectors in the domain. If that is the case, then it's going to be an orthogonal transformation. This is the basic thing. But the thing is, there are few properties, okay? If the inner product space under consideration is some r power n, okay? Is some r power n with dot products as the inner products. Now the dot, they are saying that this r power n, you are going to have dot product as your inner product for this vector space, okay? Now they are saying that an orthogonal transformation with this, by considering this r power n, will preserve the lengths and angles. What they are saying is, you have an inner product space r power n, okay? Now your inner product is usual dot product, okay? This is the given. Now if let's say if T is an orthogonal transformation from r power n to r power n, they are saying that it will preserve the length and angles, okay? This is what it's saying. So what do we mean by this? By preserving lengths and angles, okay? Let us just say one thing. By preserving length, what they mean is, like you send vector v as input, there's going to be some length for v, correct? There's going to be some length for v, okay? Now the output is t of v, okay? Now the norm of t of v, they are saying it will be equal to v, okay, for an orthogonal transformation, okay? So this is what they are saying. So we know, right, if t is an orthogonal transformation, then we know t of v comma t of u, the inner product between these two will be equal to inner product between u and v, correct? This is from the definition, okay? Now let's send v as input for both, okay? Let's send v as input for both, okay? So the output will be, the output will be t of v comma t of v, right? Sorry, the output will be t of v. Now the inner product of this will be equal to inner product of this, right? Right. So if you take the norm, this is what? This is standard dot product, right? This is your usual dot product. So the dot product between TV, dot product TV is going to be the length of TV, correct? And similarly, the dot product between V and V is going to be length of V. So when you send V as input, the output is going to be T of V. The length of V is equal to the length of T of V. Understood? Understood?
Yes.
Okay. So this is one property. Now they are saying that the angles will also be preserved. If T is an orthogonal transformation, then the angles will also be preserved. Okay. Let's say there's a vector V and there's a vector W. Okay. Now let's say unit vector of V is UV is unit vector of V and UW is unit vector of W. Okay. This is the thing which we are going to take. Okay. Now we know that the inner product between T of UV, okay, comma T of UW, since T is an orthogonal transformation, this is going to be equal to the inner product between UV and UW. Correct? This is from the definition. Okay. So the LHS will be equal to RHS. Now what is this going to be? The dot product between UV and the dot product between T of UV and T of UW. Okay. This is going to be the dot product. Okay. Now similarly, this is going to be dot product between unit vector of V and unit vector of W. Okay. So this will be equal to what? Let's say the angle between V and W is theta. Okay, VW, the angle is theta. Since these are unit vectors, we can say this is going to be cos theta, right? Correct? True or not? This is going to be cos theta, correct?
Yes.
Okay. So the dot product between TUV and TUW is also going to be cos theta. Now we know one thing, it is going to preserve the length. So this is going to be a unit vector, correct? This is going to be a unit vector and unit vector. This is also going to be an unit vector. Which means what? Theta is the angle between TUV and TUW, correct? Theta is going to be the angle between these two also, correct? So the angles are also preserved. Am I right?
So, will this work even if the inner product is defined apart from dot product?
Yeah, see, if it is an orthogonal transformation, it will. Okay, but this should be the inner product space under consideration should be some r power something. Okay, fine. The inner product space under consideration should be some r power something. Okay, I'm not sure if you take some subspace and whether this will work or not. I'm not sure, but the given property is about r power n. Okay, fine. So this is about orthogonal transformations. Clear? An orthogonal transformation is you send two vectors as input, any two vectors, v and u. The output is going to be tv and tu. The inner product between tv and tvu will be equal to the inner product between v and u. Okay, this is what we mean by orthogonal transformation. If this property is satisfied, then that linear transformation will be an orthogonal transformation. Okay, now what they are saying is, if r power n is under consideration, I'm sorry, I think Kiran, I think you asked for some other some other inner product being defined, right?
Yeah. What if the inner
Uh,
product is not standard inner product?
I
I
think
mean, a
I'm not.
standard. Yeah.
See, if it is not standard inner product, will we get the length first? Will we get the length first? See, maybe, see, if it is not standard inner product, this will be true. But will it be equal to the length? Right? That is the question. I think it shouldn't be equal to the length. Okay? Because let's say it is 2, let's assume that 2 x1, x2 plus 3x3 sorry, 2x1, y1 plus 3x2, y2. Let's say this is the inner product. Okay, of course we have to verify whether it's an inner product. Just for assumption, I'm just saying. Okay, now this cannot be the length, right? The length is just the square root of the standard dot product with itself, right? So maybe it will satisfy this. Okay, because it's going to be an orthogonal linear transformation, it will satisfy this, but this property, I
Yeah,
think
but
it shouldn't satisfy. Yeah.
no. Sometimes if the inner product is defined something else, like
Yeah.
you
That's
have
what.
given some example 3x1 y1
Yeah, then
plus
maybe
2.
it won't get satisfied. I think it shouldn't get satisfied. I think it shouldn't get satisfied. Okay,
Then also
because
norms are defined as per the inner product.
see, if you norm can be defined differently, but then length is just, but the length is defined in one way, right? Norm can be different. Norm is a function, right? But length is like, you can understand the difference, right?
It's a special
Length
norm.
is, yeah, it's a special norm. Length is a norm, but all norms are not lengths, right? See, length means
Yeah.
we can physically measure and see. Okay, length is something we can physically measure and see at least until R3, right? So I think if the dot product is different, like, sorry, if the inner product is not the dot product, then I think it shouldn't satisfy. It is something else, such that the length, it is not, it is, if it is not the dot product, I think it shouldn't be satisfied because the length will be different in that case. Sorry, the length will be the same, but the norm which we get might be different. The length, like what I'm saying is, just for assumption I'm saying, okay, just for some considerations I'm saying, let's assume 2x1, let's say x1 y1, okay, and x2 y2, okay. Now let's say this is equal to some 2x1 y1 plus 3x2 y2, okay. Of course we have to verify whether it's an inner product or not. Right now I think just for explanation, let's assume that this is an inner product. If you want, you can go and verify. We'll just verify, okay. But we are assuming that this is an inner product, okay. But considering this, we cannot say, right, the inner product between v and v, with this definition, the square root of this cannot be the length, correct? It cannot be the length, right? Even though this is the inner product, this is not the length, okay. Maybe the norm is defined like this, but the length is different, right? Okay. I think such a question will not be asked, but even if it is asked, I think it shouldn't be the case because the length will be different. Okay. This is not the length, right? Anyways, this is not the length, anyways, under this consideration. Okay. Fine. But then what we need is, under this case, it will preserve. Okay. That's all I think I can say right now. Like, I just want to know if a session on this is over by the instructors. Is it over? A session on this, is it over?
No, sir.
Okay, maybe I think you can ask this there because I have not read about your doubt. I think it shouldn't be, but I think you can just verify it with the instructor in the next class. Okay.
Okay.
All I can say is this is true and I have given the proof. Okay. That's all I can say, but I think it shouldn't be true. Okay. From this reasoning, I think it shouldn't be true. Yeah. Okay. So with this, can we go to the questions? Hopefully, I think we can go. Yeah. So the first thing, the linear transformation for everything is going to be from R2 to R2, okay, for all the 4 options. Okay. Now, first they are saying T is a linear transformation. Okay. Where here R2 is the inner product space with usual dot product. Okay. Then will the dot product between TU and TV, will it be equal to the dot product between U and V if this is a linear transformation? For just linear transformations, will this be equal? For a linear transformation, will this be equal always?
No.
Like for example, T of xy is equal to x0, okay. Then this is not the case, right? Everything will lie on the x-axis, so the angle should be 0, right? So this is not always true, okay, because it's just a linear transformation. Whereas for the second one, it is an orthogonal linear transformation, right? For an orthogonal linear transformation, okay, the inner product space is again R2 and the inner product is the dot product, okay. Then T of U dot product T of V is equal to U dot V, right? So this should hold for orthogonal linear transformations, correct? Right? That's what we saw from the definition. Okay. So the second one is correct. Now for the third one they are saying again R2 is the inner product space, and now the inner product is given by this one, okay. T of AB is 2A1B1 plus 5A2B2, okay. This is the inner product, okay. Now again they are claiming that the inner product between TU and TV will be equal to UV. This is what they are claiming again. Is it true for a linear transformation that this will always be true? Again, not necessary, right? Right? Again, you can take this example again. Let's say T of xy is equal to x0. Okay. Let's take 1, 1 and 1 minus 1. Okay. Let's take V is equal to 1, 1 and U is equal to 1 minus 1. Okay. Now, this is not an orthogonal transformation. Okay. Like the codomain is R2, but then the range is just this one. Okay. So what is T of u? T of u is going to be 1 0, and T of v is also going to be 1 0, correct? Because both 1 1 and 1 minus 1. For both, the linear transformation with respect to this definition is going to be 1 0 and 1 0. Correct? So if you take dot product between Tu and Tv, Tu dot product, sorry, inner product Tv. Now what is the inner product given there? The inner product given there is u comma v is equal to, sorry, they have given a comma b is 2a b1, 2a1 b1 plus 5a2 b2. Okay.
So, however, the length will not be preserved. So, from
Yeah, the length will not be preserved because the inner product here is not the dot product. Okay. So this is the thing. From this we can see it is going to be 2 times 1 times 1. Okay, plus 5 times 0 times 0 because a2 b2 are these zeros. So this is going to be 2. But with respect to the inner product between 1 minus 1, okay, with 1 minus 1, I'm sorry, with 1 minus 1 and 1 and 1, okay, the inner product between these two is going to be 2 times 1 times 1 plus 5 times minus 1 times 1, okay. This is going to be 2 minus 5, which is minus 3. So LHS is not equal to RHS, right? So this is not always true, okay, fine. But for an orthogonal linear transformation, this will be true, correct? Am I right? For orthogonal linear transformation, from the definition we know the inner product of the output vectors is going to be equal to the inner product of the corresponding input vectors. Right? This is something which we know. Since they have given that T is an orthogonal linear transformation, okay, we can say this is going to be true, right? Okay.
but it's not orthonormal, right? Or like
No, the question is
the inner
orthogonal linear,
product.
orthogonal transformation. Yeah.
Yeah, that's fine. But the inner product is defined something else from the
That is
dot
fine.
product.
See, the inner product can be anything, okay? The inner product can be anything. But not for all inner product will this property be satisfied. Fine. For they have given that for dot product and for R power n as domain and codomain, it will be satisfied. Okay, but this is
Oh,
satisfied for all orthogonal transformations, right?
okay, fine.
This is from the definition, and this is a special case. Okay. This is a special inference which you can draw under a certain circumstance. Okay. Fine. Yeah. Okay. So this is first one. Now, this one, do you all know about orthogonal matrices?
No.
No.
Okay, fine. See, the orthogonal matrices, it's given here. The thing is, one second. Yeah. Rotations. Yeah, here. Okay. The orthogonal matrices. Okay. Now they are saying A is a matrix representation. Sorry. Yeah, matrix representation of an orthogonal linear transformation. T is an orthogonal linear transformation. The one which we saw just now. Okay. Now A is the matrix for this. Okay. With respect to again an orthonormal basis. Let me make this clear. See, T is an orthogonal linear transformation. Okay. Orthogonal linear transformation. Okay. Now, A is the matrix representation with respect to an orthogonal basis, orthonormal basis. A is a matrix representation. Matrix representation. Okay. With respect to orthonormal basis. Okay. with respect to orthonormal basis. If this is what we have as given, then A will satisfy this one. Okay, what they are saying is A will satisfy A times A transpose will be equal to A transpose A, and this will be equal to identity matrix. Okay, this is given. From this given, we can say this is true. Okay. Now if now this is given. Now coming to orthogonal matrix. Okay. I'm sorry. An orthogonal matrix, any matrix which satisfies any matrix A which satisfies this is an orthogonal matrix. Okay. A matrix A satisfying A transpose is equal to A transpose A is equal to identity matrix is an orthogonal matrix. Clear what an orthogonal matrix is? You take a matrix, you find its transpose. When you multiply matrix A with its transpose, you have to get the identity matrix. And if you multiply the transpose with the matrix itself, again you have to get A. Okay. Clear, right? That's all is there. There's a matrix, you take the transpose, you multiply both, you're going to get an identity matrix. And you take the transpose and the matrix, you multiply it. Then also you're getting identity matrix. If that is the case, then the matrix is an orthogonal matrix. Okay. Now if A is the matrix representation with respect to orthonormal basis for an orthonormal linear transformation, then this matrix will satisfy this. Clear? That is, if A is the matrix representation with respect to orthonormal basis for an orthogonal linear transformation, then matrix A will be an orthogonal matrix. Okay.
And the vectors should be orthonormal set of vectors, right?
Like what they are saying is, coming to orthonormal vectors, they're saying for a matrix A is orthonormal. Okay. If and only if A transpose is equal to I. What they're saying is, the rows of A are orthonormal. Okay. If and only if A transpose is equal to I. For some matrix A, okay, the rows are going to be orthonormal if A transpose is I. Note that the rows of matrix A are orthonormal if and only if A transpose is I. Okay. Now the other thing for columns. Again, columns of A for some matrix A, not with respect to these and all. For some matrix A are orthonormal. Orthonormal if and only if A transpose A is identity matrix. If and only if A transpose A is equal to identity matrix. Here it is A transpose and here it is A transpose A. Okay. Hope that was clear, right? Okay. So the thing is, it's like this. Okay. Let's say for columns, let's say these three columns are orthonormal. Okay. Now when you find A transpose, what will this be? These will be these three row vectors, right? Now this is the transpose. This is the transpose matrix of this one, and this is going to be this matrix itself. Okay. Now if these three are orthonormal, what is the case? What is going to be like? See, the dot product between this vector and this vector is what? This is, let's say this is v1, v2, v3. Okay.
Yeah,
Okay.
it
This
is
will be
the
v1.
product of the column, the vectors.
Yeah. This is v1, v2, v3, and this is also v1, v2, v3. Now the first entry is the dot product between this vector and this vector. If this is orthonormal, that is here, if these three vectors are orthonormal, then they are going to be unit vectors first. So unit dot product of v1 with v1, it's going to be norm square, right? If norm is 1, then the norm square is also going to be 1, so this will be 1. Similarly, the dot product between these two, it's going to be 1 here. Similarly, dot product between these two is going to be 1 here. Okay. Now v1 dot product v2 will be 0 because they are orthonormal. v1 dot product v2 will also be 0. v2 dot product v1 will be 0. So the remaining things are 0. Okay. This is for columns, and for rows, I think you can try and see. Maybe for rows, I think this is not the way you would be able to go, because A will be row vectors, A transpose will be column vectors. I'm sorry. Yeah. A transpose, right? A is row vector and A transpose is column vectors. Now I think you can multiply again and see. Okay. So this is what they're trying to say. Okay. This is what they're trying to say. Thus, for an orthonormal matrix, the rows form an orthonormal set and the columns also form an orthonormal set. Okay. For an orthonormal basis, sorry, for an orthonormal matrix, both are going to get satisfied. Am I right? Because that is the definition for an orthonormal matrix. Okay. See, you should read it like this. Okay. Till this line, okay, this is an observation. Okay. Till this shading part, it's an observation. This part you can maybe take it as a some definition for an orthogonal matrix. Okay. And this one you can take it as some observation again. And this one can be taken as a conclusion. This is how you read this. Fine. So with this, I think we can go to the second question, right? Okay. So for second question, now A is the matrix representation of an orthogonal matrix. Okay. From R power n to R power n, then choose the correct options. Okay. See, here they have given with respect to some orthonormal basis, right? Remember, I think it was there in the notes also. If nothing is, no information about the basis is given, we have to take standard normal ordered basis, right? If no information is given, we'll just take the standard ordered basis, right? And the standard ordered basis is orthonormal, correct? Okay, so we'll take with respect to standard ordered basis. If that is the case, then A is going to be an orthogonal matrix, correct? If some other basis is given, then we have to check and see. If orthonormal basis is given, we can say, right? We can say that matrix A is orthogonal matrix. Now, if A is an orthogonal matrix, the first option will be true, correct?
Yes.
Okay, the first option will be true. Okay. Now the second, look at the second option. They are saying A is equal to A. They're saying the second option is A will be equal to A transpose. See, first thing, if something is an if A is an orthogonal matrix, then we know A transpose will be identity matrix. A transpose A is equal to identity matrix. Okay. Fine. Can we always say now, can we always say that this will be true? That is, A is equal to A transpose. See, if A is identity matrix, this is going to be true, right? I is equal to I transpose, this is true. But for any such matrix, can we say that?
No.
Like, the thing is, A transpose is equal to I, okay? Now, even if you multiply A transpose here on both the sides, you are going to get A transpose A is going to be identity matrix. You will get A transpose is equal to A transpose. And one more thing, like the inverse will be unique, okay? For an invertible matrix, the inverse will be unique, okay? So A transpose is technically the inverse of A, correct? And A is the inverse of A transpose. So it's like an inverse, okay? Fine. Okay. So second one is not always true. The third one is A transpose an upper triangular matrix,
Yes.
right? Because A transpose is going to be identity matrix. Identity matrix, we know it's an upper triangular matrix. It's a scalar matrix, but it's also an upper triangular matrix. Okay. So third option is correct. And fourth option says it's a lower triangular matrix. This is also all correct, right? It's a lower triangular matrix. Okay. Because everything above the diagonal is 0, or everything to the right of the diagonal is 0. That's a better way to say. Okay. So fourth one is correct. And A transpose is equal to A inverse. This is also correct, right? Because see, if A transpose is equal to I, then we can say the rows are orthonormal. Correct? If A transpose is going to be identity matrix, then the rows of A are going to be orthonormal. If they are orthonormal, then they will be independent, right? They'll be independent, right? These three rows will be linearly independent. Okay. So we can say, and notice one more thing. A is from the domain and codomain are the same thing. Okay. So the dimension of the matrix, this is going to be a square matrix also. Okay. So then this will be invertible, correct? Then A will be invertible. I'm just saying why it should be an invertible matrix. Okay. If it is
And
invertible,
all orthogonal matrices should be invertible.
yeah, or all orthogonal matrices should be invertible. But here I'm just giving some reasoning. Okay. So it should be invertible. It should be invertible. So we'll have an A inverse. Okay. And we know that A inverse is equal to I. We also know the inverse should be unique, right? Your inverse should be unique, or you can equate both. A times A transpose should be equal to A times A inverse. Okay. Multiply A inverse on both the sides. You will get A transpose is equal to A inverse. Okay. I just wanted to say that it is invertible. Okay. So this is correct. If this is equal to A inverse, it's not going to be equal to minus of A inverse. Correct. That is also there. It's equal to inverse, it's not going to be equal to the minus of its inverse. So this one is not clear. Sorry, this one is not true. And A inverse does not exist, they are saying. A inverse does exist, right? We have seen that A inverse does exist because it's invertible. So this option is again not true. And the last option is A inverse is also an orthogonal matrix. Is it true? A inverse, what is A inverse? A inverse is your A transpose, right? We know that A transpose is equal to I. A transpose A is also equal to I. So if we can say A is an orthogonal matrix, then A transpose should also be an orthogonal matrix. Clear? So the last option is also correct. Okay. And for second option alone, I think we have to show an example. Okay. Just like that, we have told that it is not necessary, but then I think we need an example. Can somebody come up with an example? Let's say in 2 cross 2. Okay. Let's say in 2 cross 2, we need some matrix. Okay. Let's say we need this is A and this is A transpose. Okay. There'll be 2 rows and 2 columns. And this will be identity matrix. 1, 1. Okay. Now we want it in such a case that A is not equal to A transpose. Okay. Can like, is it possible? See, like, one thing we know is what is 1 by root 2 comma 1 by root 2? 1 by root 2 comma 1 by root 2. What is this? It is it's a matrix. It's a vector with length 1, correct? 1 by, if you take square of first term, will be 1 by 2. Square of second term will be 1 by 2. Add these two, will get 2 by 2. You'll get 1. So this is like you have 1 comma 1, and 1 by root 2 comma 1 by root 2 is the unit vector form of this, right? So let's say we have this as the first row vector, okay? 1 by root 2, 1 by root 2. So if this is the first row vector, here it should be the first column vector, okay? So 1 by root 2, 1 by root 2. So this is your first column vector. Now we need some vector here such that these two vectors are orthonormal, okay? Only then we can put it here so that we get 0 here. What can be an orthonormal vector for this? Any idea what can be an orthonormal vector for this? Like is minus 1 by root 2 or 1 by root 2, is this orthonormal? It is orthonormal, right? Sorry, this is orthogonal to this, correct? This is going to be minus 1 by 2. This is going to be 1 by 2. That is, I'm taking dot product. And when you add those two, you are going to get 0. Now, if you put this as column here, minus 1 by root 2. Okay. So what we can do is maybe like we need some two unit vectors such that the transpose is not the same. Okay. This is what we are trying to see. Any idea? Like we have to have some example, right? Only then we can say this is not correct. Or this is correct means it should always be true. Let's take some 1 second. Okay, let's go to Desmos and we'll have x square plus y square is equal to 1. Okay. Let's take some other vector. Okay. Now we can see that 1, 2 and minus 2, 1, these two are orthogonal, right? So we can take unit vector of these two and we can put those as columns and we can see as rows and we can see whether we are getting symmetric thing or not. Okay. Like we should show an example. If it is wrong, we have to show an example, right? That's what I'm saying. So what is going to be the unit vector of 1 by 2? The unit vector of 1 by 2 will 1, 2 will be 1 square plus 2 square. This is going to be 5. So root 5 we have to take. So it's going to be 1 by root 5, 2 by root 5. Okay. So we can have 1 by root 5, 2 by root 5. Okay. Now something orthogonal to this will be 2, 1. I think however we take, it's going to be like this. Okay, for second one alone, can I just, at the end of the class, can we just see, after seeing maybe a few more questions? Fine. Because for second one, I think we have to prove whether this is not prove that this is not always true. Okay. Or we have to prove that this is always true. That is A is equal to A transpose. We'll see this option alone last. Okay. We can go to other questions. The third one is if A is the matrix representation of an orthogonal transformation, then choose the correct statements. Okay. The column vectors of A are orthogonal, but not orthonormal. Okay. Again, this question also you have to take with respect to standard ordered basis, right? You take it with standard order basis, it's going to be orthogonal matrix, right? Am I right? It is going to be orthogonal matrix, right? Hello. Kiran, others, are you all there?
Yeah.
Yeah. See, like for third one, A is the matrix representation of an orthogonal transformation. Okay. From R power n to R power n, then choose the correct statements. The column vectors of A are orthogonal, but not orthonormal. Is it? See, if A is the matrix representation of an orthogonal transformation, they have not given a basis, so we can take the standard ordered basis, right? We take the standard ordered basis, we can say that this is an orthogonal matrix. If it is an orthogonal matrix, we can say the rows and columns both are orthonormal, correct? Okay, both here we saw, right? For an orthogonal matrix, both rows and columns are orthonormal. And why we are assuming this as an orthonormal basis, because orthogonal matrix, is because we are assuming the basis to be standard ordered basis. Okay. Yeah. So these two will be correct. For the fourth one, we have to find which vector is orthogonal to these two vectors. Okay, there's a set B. We have two vectors. Find the third vector which is orthogonal to both the vectors in B. We just have to multiply and look at the dot product. I hope this question is simple. Right? You can just find the dot product and see. Okay. Now the fifth question is, we have to again take the same set B. Okay. And the vector obtained in question 4. Okay, question 4, which is orthogonal to set B. Okay, we have to take these two vectors and we have to take one from the options, the option whichever is correct. Okay, the option which is correct will be orthogonal to both, correct? Now, with these three vectors, we have to form columns of an orthogonal matrix U by scaling these vectors. See, if U is an orthogonal matrix, then what can we say about U? The columns will be orthonormal, correct? If U is an orthogonal matrix, then the columns will be orthonormal. So what we have to actually do is, we have to take these two vectors. Now, which vector will be orthogonal to these two here? Just we can multiply it with the second vector and see whichever is first. We can just eliminate few vectors. Let's start with last. -1, -1, and -2. So -1 times -1 is 1. Or can I write it there? I think I can write it here. 1, 1, -2. Okay. Sorry, 1, 1, 1. Okay. 1, 1, 1. Then -1, 1, 0. Okay. -1, 1, 0. Now what we have to do is we have to choose the vector which is orthogonal to these two. Take -1, -1, 2. -1, -1, 2. The dot product between -1, 1, 0 will be -1 into -1, 1. -1 into 1 is -1. 2 times 0 is 0. Okay, so 1 -1 plus 0 is going to be 0, right? So with this one, it is fine. Now again, we'll do it with the first vector. -1, -1, 2, dot product with 1, 1, 1. Okay. So we have to do -1. Sorry, this is 1, I think. Sorry. Yeah. -1, -1, -2. Yeah. I'm sorry, this is -2. Okay. Here also I've taken 2. Sorry. Really sorry. Here it's -2. Okay. Let me do it again. Like we have -1, -1, -2. The dot product with 1, 1, -1, 1, 0. We'll first take dot product with this. Okay. So you will get 1, -1 plus 0. Okay. -1, -1 is 1. -1, 1 is -1. -2, 0 is 0. Okay. So this will be 0. Now we have to check it with the first vector also. So -1, -1, 2. The dot product with 1, 1, 1. Okay. So this will be -1, -1, -2. Okay. You have to add all the three. Sorry. You have to add all the three. These commas are not necessary. Sorry. If you add all the three, you'll get -4. Okay. So here this is not orthogonal to the first vector. So option 4 is wrong. Okay. And look at option 3, -1, 1, -2. Okay. Again, you can multiply it with the first vector. -1, 1, -2. Dot product. Sorry, the dot product with the first vector will be -1 plus 1 -2. This is going to be -3 plus 1 -2. So this is not orthogonal to the first vector. So this is wrong. The second option, look at this second option. This is just -1 times this, right? So if this is not orthogonal to this vector, then this is also not going to be orthogonal to this vector, correct? Am I right? I hope you.
Yes, sir. It's
Yeah. So this is
really
wrong. Okay. So the first option is 1, 1 minus 2. Okay. First option is 1, 1 minus 2. So if these three are wrong, that should be correct. Anyways, we can multiply it and see. So 1, 1 minus 2 with 1, 1, 1 is 1 times 1 is 1, the dot product. Okay. And 1 times 1 is 1. Minus 2 times 1 is minus 2. So this is 0. 1 plus 1 minus 2 is equal to 0. So first one is fine. Next is 1, 1 minus 2, the dot product with the first vector, second vector is minus 1, 1, 0. Okay. So minus 1, 1, 0. Okay. So 1 minus 1 is minus 1. 1, 1 is 1. Minus 2 times 0 is 0. So this is going to be minus 1 plus 1, 0. So this is orthogonal to both. Okay. So what we have to do is, we have to take these three vectors, add them as the column vectors of U. Okay. In such a way that they are such a way that Q is an orthogonal matrix. Okay. We'll have it as the column vectors. Okay. We'll have those three vectors as column vectors. But the thing is, if U has to be an orthogonal matrix, then the column vectors have to be orthonormal. Correct? If Q has to be orthogonal matrix, then the column vectors have to be orthonormal. Okay. So what we have to do is, you have to find the unit vector form of these three vectors and we have to put them in the columns. Okay. So I hope that should be easy for you, right? What we have to do is take these vectors in this order. Okay. First vector, second vector, third vector. Okay. You have to find the unit vector for these three. Okay. Take their length, divide it by their length. You will get the unit vectors. I hope everybody knows that. Once you get the unit vectors, put them here. Okay. Put them as the column vectors. Okay. And see which is correct. Okay. So this one, I think right now we don't have time for calculation. Hope this one can be done by you, right? Yeah. I hope this is not so difficult. So this is fifth one. And after fifth one, you have to do sixth one also. Okay. So the sixth one is, there's a vector V. What you have to do is, you have to choose the correct option. The correct options are like this. You have to find the length of V. Okay. One thing is, you have to find the length of V. Next, you have to find the length of U times V. Let's say this matrix is, let's say one of these matrices is correct. Okay. You multiply that with this vector. Okay. Take this as column vector and multiply. Okay. So it's going to be a 3 cross 3 matrix times 3 cross 1 vector. Okay. You multiply these two, you'll get a vector. That is going to be UV. Okay. That is going to be UV. You multiply these two. Sorry. You multiply these two, you find the length of that vector and see whether these two are equal or whether they are not equal or whether these equations are satisfied. You have to just check. Okay. You have to multiply and find their length and then check. This is also not so difficult, right?
Yes.
Yeah. Fine. And for the last one, find the matrix representation. Okay, this one I think what we have to do is, okay, the matrix representation of T is U. Okay. Matrix representation of T is U. And there's a matrix B. Now what you have to do is, first you have to see if T is an orthogonal transformation. Okay. They have given the matrix and they have given that U is the matrix representation and it is this one. Again, they have not given what the basis is, so you can take the standard ordered basis. Okay. You can take the standard ordered basis. Okay. So how will you prove that T is an orthogonal transformation? How will you prove it's an orthogonal transformation? See, one thing is, either you need the inner products. Okay. If nothing is given, of course you can take dot product, but you don't know what the definition of the transformation is, right? T of x comma y comma z is equal to this. That thing you don't know, right? So you don't know what the output is. So what you can do is, see, V is an inner product space. Okay. T is a linear transformation from V to V. Okay. And it's an orthogonal transformation if this is true. This is one way to do. The other thing is, from this definition, what can you say? with respect to an orthonormal basis for V, okay, if A is the matrix representation of linear transformation, then you can say it's an orthogonal matrix, right? You can say A is an orthogonal matrix. Now, so what you can do is check if U is an orthogonal matrix. Okay, we know that the basis is an orthonormal basis. If this is an orthogonal matrix, then you can say T is an orthogonal transformation, correct? Like what I'm saying is, for those who don't understand, what I'm saying is, you have T, you have U, okay, and you know basis is standard ordered basis, okay, standard ordered basis. Now what you have to do is you find if is U orthogonal matrix, okay, you have to find this. If U is an orthogonal matrix and it is with respect to standard ordered basis, you know this is an orthonormal basis, right? Orthonormal basis, standard ordered basis, okay. So in that case, T will be an orthogonal transformation, because if T is an orthogonal transformation and if the basis is standard, if the basis is an orthonormal basis, then you can say use an orthogonal matrix. So the other way around also should be true, right?
Yes.
Okay, so that's what we are doing. You have to find that. You have to, if that is the case, then T will be an orthogonal transformation. Otherwise, it will not be. And you can see B is a symmetric matrix, right? B is a symmetric matrix. U inverse BU, again we have to multiply these things. You have to find U inverse. If it is an orthogonal transformation, you can just find the transpose to find the basis. Sorry, you can just find the transpose and you will get the inverse, right? You have to multiply everything and see and which of the following options are correct. Okay, understood. This is, again, you have to do a lot of calculations, that's all. In terms of concepts, it's not really difficult, okay?
Yes.
Yeah. And that's all, but then we have to just see if we can find an example for this, okay? First, let's check the answers, okay? I think it should not always be true, but we have to find an example for this. Okay, yeah, this is correct, but then this, if this is wrong, we have to find an example. Maybe we'll just try once. If we can find, we can have it. Otherwise, in the next class, I'll ask the TA to just give an example for this, okay? Or I'll put it on the discourse, okay? We'll just try once and see. Okay, what we need is, we see that A is an orthogonal matrix, okay? From those explanations, we say A is an orthogonal matrix, okay? Now what we want to prove is A transpose is not equal to A, because of course the option is saying it's not correct, okay? So we have to prove this. So how will we prove this? Like, if A is equal to identity matrix, it's going to be true, right? The transpose is also going to be the same. I think for a 2 cross 2 matrix, that's the issue. I think for a 2 cross 2 matrix, if you take something, then symmetrically it will come. Let us take some 3 cross 3 matrix, okay? And we need some transpose, okay? This is matrix A and we need the transpose such that the resultant is identity matrix, okay? And we don't want A is equal to A transpose. We just want to find one such example. We don't want both to be equal. But of course, A transpose is equal to A transpose. That is fine. So we just need some 3 unit vectors. Let's take for 1, 1, 1. Let's say what will be the unit vector? 1 by root 3, 1 by root 3, 1 by root 3, correct? Okay. So this is A, and A transpose will be 1 by root 3, 1 by root 3, 1 by root 3. Okay. Now, if this is, let's say, 3D, yeah. So we have, sorry, we have 1, 2, 3. So we need something orthogonal to this, right? What can be orthogonal to 1, 1, 1? I'm sorry, for 1, 1, 1. I'm sorry. For 1, 1, 1. What can be orthogonal to this? 1, 1 minus 2 can be orthogonal, right? 1, 1 minus 2. Right? The dot product of this will be 1 plus 1 minus 2. Right? So you can take 1, 1 minus 2. What will you get? What is the length of this? 1 square plus 1 square plus 4. Right? Sorry. Yeah. So this 1 plus 1 plus 1. Sorry, 4. This is going to be 6. So length will be root 6. Okay. So you can have 1 by root 6. 1 by root 6 and then minus 2 by root 6. Okay, you can put this here. So 1 by root 6, 1 by root 6 minus 2 by root 6. Okay, so this first column vector, sorry, first this row vector, when you multiply, you're going to get this 1 here. Okay, now if you take this second row vector and multiply it with first row vector, you're going to get 0 because they are orthogonal. Okay, now you just need one more orthogonal vector. For these two, you need one more orthogonal vector. Okay, you need 1, 1, 1. You have 1, 1 minus 2. So what else can be the thing? 1, 1, 1. You can, of course, you can do projections and you can see 1, 1 minus 2. Yeah, you can take the null space, right? You can take the null space of this 1, 1, 1, 1, 1 minus 2. R2 minus R1. Okay. So what will you get? 1, 1, 1, 0, 0, minus 3. Divide this, you will get 1. Divide this by minus 3, you will get 1. And if you subtract these two, you will get R2, R1 minus R2, you will get 0 here. Okay. So this is in reduced row echelon form. So from this, you can see x plus y should be equal to 0 and z should be equal to 1. I'm sorry, z should be equal to 0. Okay. So z should be equal to 0. If x plus y should be 0, then y is equal to minus x, right? So minus x, sorry, x minus x, 0. Is it orthogonal? Let's say from which is of this form. If x minus x and 0, you'll get 1 minus 1, 0, right? Is 1 minus 1, 0 orthogonal to these two? 1 times 1 is 1, 1 times minus 1 is minus 1, and 0, the third element will be 0. So you add 1 minus 1, 0, and same for here also, right? So 1, 1, 1 minus 1, 0 is orthonormal to both the vectors, correct? Clear how we got 1 minus 1 and 0?
Yes.
Yeah. Now we need the unit vector form of this. Okay. So the length will be 1 square plus 1 square plus 0 square. This is going to be root 2, right? The square root of this. So this will be 1 by root 2 minus 1 by root 2, 0. Okay. So you can write this here also. 1 by root 2 minus 1 by root 2, 0. Now product of these three will be identity matrix, correct? Am I right? You can see that this row vector, this column vector are same. They are, and we know the length is 1. So when you do dot product, you are going to get 1. And we know the first vector and these two vectors are orthogonal. So this will be 0. The second vector and first and third vector are orthogonal. So these two will also be 0. Second row vector, multiply the dot product with second column vector is going to be 1. Okay. Similarly, for third row vector and first column vector, again they are for first column vector and third row vector, again they are orthogonal. So this will be 0. Third row vector and second column vector, again they are orthogonal. So this will be 0. And at last, third row vector, dot product with third row vector is going to be 1. So clear? And look at the transpose. And is the transpose the same? Here 1 by root 3 is there, and here 1 by root 2 is there. So the transpose will not be equal to itself. Okay. So hope I have given an example. Like, was this method of how I came up with the example fine for you? Okay, the thing is,
We have to find a orthonormal set of vectors.
yeah, we need orthonormal set of vectors such that when you put them as row vectors, okay, and we have to check also if the column vectors are, yeah, if A transpose is this one, but again we have to check if column vectors are orthogonal. Oh, that is also there. So we have to check if column vectors are also orthogonal. Only then it's an orthogonal matrix, right? Sorry, if we have to check if column vectors are orthonormal. So one, okay, I think this should not. Just try and see, okay? I'm not sure. Like, maybe on
So,
Python we have, yeah.
sir, we can take 1 by root 2, uh, 1 by root 2 and 0 as the first column. And for the second column, we can take 1 by root 2, minus 1 by root 2 and 0.
1
And
by
for
root
the
2, 1 second,
uh,
minus 1 by root 2, 0, okay. Second one,
um,
yeah.
can you write column wise? Yeah.
1 by root 2 minus
1
1
by
by
root
root
2,
2,
1.
0,
No,
okay.
1 by root 2.
Here
The
also,
second one. The second one is 1 by root
okay,
2
okay, yeah,
and 0.
okay.
1 by root 2 minus 1 by root 2, 0.
1
Column
by
wise.
root 2 minus 1 by root 2, 0. And the third one is 0, 0, 1. Huh?
Yeah, 0, 0, 1.
No, then the transpose will be same, right? We don't want the transpose to be same. That's the issue. Here we have seen that A transpose is equal to 0. Okay. Sorry, identity matrix. We have also seen that the transpose is not the same, but we should also see if A transpose is equal to A. That is also that. Sorry, A transpose times A is equal to identity matrix. This is also something which we have to see. A transpose times A. Is this also identity matrix? Let's just do dot product for the first column and see. First column and first row. Okay. 1 by root 3, 1 by root 6, 1 by root 2. Okay. 1 by root 3, 1 by root 6, and 1 by root 3, 1 by root 2. Okay, we have to just do dot product with itself. So this will be 1 by 3 plus 1 by 6 plus 1 by 2, right? So this is going to be 2 plus 1, 3, and this is going to be 3. So 6 by 6, this is going to be 1. So the first column is unit vector, okay? First column is an unit vector, correct? See, right now I just took the dot product and saw 1 by root 3 square is square of 1 by root 3 is 1 by 3, square of 1 by root 6 is 1 by 6, and square of 1 by root 2 is 1 by 2. Add these three, you will get 1. Similarly, for second one also, 1 by root 3, 1 by root 6 minus 1 by root 2. So here when you square this minus will become plus. So you're again going to get the same one, you will get 1. And similarly for the third one, 1 by 3 root 3 minus 2 by root 6. Okay. So square of this will be 1 by 3. Square of this will be 4 by 6. Okay, here you're getting 5 by 6. Okay. So then,
Sir, we can take a 2 by 2 matrix.
see, that's what the
In this
two
case.
the thing is for 2 by 2 matrix. For 2 by 2 matrix, let's say x square plus y square is equal to 1. Okay. For this, let's say with whatever corresponding to whatever two matrices you take, the 90-degree is just like, you know, the coordinates are interchanging and we are getting negative. Right? Let's say, see, 2, 1 and 1 minus 2, like those two are orthogonal. 2, 1 and minus 1, 2, they are also orthogonal, correct? But this is just like interchanging and sign is changing for one of those, right? So if we put them as a matrix, like we are getting, the transpose. Oh, sorry. 1 second. 2, 1 minus 1, 2. 1 second. So what is the transpose for this? I'm sorry. What is the unit vector for this? 2 square is 4. 4 plus 1 is 5. The unit vector will be 2 by root 5, 1 by root 5. Then, okay, I think they should be like this. 2 minus. Then the columns will not be orthonormal.
So there's 0, 1, 0, minus 1, 0, 0, and 0, 0, 1.
0, 1, 0, minus 1. Sorry?
0, 0, 0, 0,
Okay.
1. So that the norm will, the length will be 1, no, for this anyway.
Okay, length is 1. And it looks like they are orthonormal. But what is the transpose for this? 0, 1, 0, minus 1, 0, 0, then 0, 0, 1. Okay?
And we have to just see if it is identical.
Yeah. Yeah. Multiplying these two will get 1. These two is going to be 0. And these two is going to be 0. Yeah. And these two again 0. Yeah. 1, 0. Yeah, I think we are getting. So this is an example. Thank you so much. Yeah. Yeah, see, yeah, this is an example, okay? As somebody has given 0, 1, 0, minus 1, 0, 1, 0, 0, 1. Okay, sorry, I'm sorry. 0, 0, 1. I'm sorry, this should be 0. Okay. Now the transpose of this will be 0, minus 1, 0, 1, 0, 0, 0, 0, 1. Now if you multiply these two should be 1. It should be an identity matrix, okay? And notice that the A is not equal to the transpose. Okay. Okay, then it should also work for 2 by 2, right? 0, 1, minus 1, 0, then 0, 1, minus 1, 0. Now also it should work, right?
Yeah.
Oh, we have missed a simple example.
Yeah, this will also work 2 by 2.
No.
No?
No. Minus 1 times 1. Okay. I'm sorry. Minus 1 times minus 1 here. Okay, sorry. Yeah, it should be fine. Yeah. So I think, sorry guys, we have missed a simple example. Okay. And thank you so much. Yeah. Okay. So this is, yeah. So this is an example of why this is not correct. Okay. Fine. Okay. Any doubt? Is there any doubt? Okay. If not, then we can leave.
Thank you.
Yeah. Thank you so much. Hope you people have understood. Yeah.
Thank you, sir.
Yeah. Thank you so much. Okay. Bye.